Cool. So we're going to talk about minimum cut algorithm on a flow graph and its implementation on image segmentation. So just to recap what flow graph is, in a flow graph, the weight of each edge indicates how much element can flow through that edge. So for example, in a diagram shown, if there is a directed edge from node A to B with weight value of 10, then a maximum of 10 elements can flow from node A to B. So, and what is a minimum cut? So generally a cut in a graph is essentially any proper subset of edges such that once those edges are removed, it generates two disjoint grooves when removed, two disjoint grooves. So for example, in the diagram on the left, if we select two red edges as a cut, once we remove that, we create two subsets, two distinct graphs that are not joined. So for a flow graph with the source and the sink, where source is the node S and the sink is the node T, a minimum cut is a cut that separates source and sink into two disjoint subgraphs, such that the directed edges in the cut flow away from the source, and the sum of the weights of the edges involved in the cut is minimum as possible. So if you look at the diagram here, the cuts involved, so a minimum cut in this case is the 12, 7, and 4. Once, as you can see, that all three edges flow away from the source, and once these three are removed, it creates two distinct disjoint graphs. So how do we find the minimum cut in the directed graph? So first we start with a graph where we define S as a source and T as a sink. We create a residual graph based on this graph. Essentially, it will look identical, but as we update, we'll explain how the residual graph is different from the original graph. So if we find all possible paths from the source to sink in the residual graph. So one example is we from source S, if we take the path 16 to A, 12 to B, and then 20 to T, that's one path. But then the thing is that the maximum flow that can happen for each through this path is 12 because of the minimum flow, because the maximum flow is essentially the minimum of all three edges. So we up in our original graph, we update how much are flowing through each edge. So in the left graph, we say right now for each edge from S to A to B to T, there's 12 elements flowing through, and the residual graph will update accordingly, except that it has the ability to undo a flow. So what this means is that there's maximum of the maximum flow that can happen from S to A, for example, is 16, and if we flow 12, we can after we flow 12, we can only flow only four elements to S to A from S to A, and if we ever want to undo the flow that we did from S to A, we indicate with the reverse directed edge with the same flow amount. So same goes for A to B. Like as you can see, we sent 12 elements from A to B, so that means that there's no edge from A to B, but then we can undo this flow by indicating a flow from B to A with the weight 12, and with similar logic from B to T. So we continue this until there's no path from source to sink in the residual graph, and this is what it's actually going to look like after multiple iterations. And from the residual graph, we find all nodes that are reachable from the source. So from S, we can reach A and C and D. And then from the residual graph, we select from the original graph, we actually select all edges going away from these selected nodes to non-reachable nodes in the residual graph. So we know we can't reach A to B, and so we select this edge. So we select this edge. And similarly for D, there's edge from D to B and D to the actual thing. So there's three edges total, 12, 7, and 4. And once we remove these this set of edges are the edges in the minimum cut, and therefore the minimum cut for this directed graph will be 23.
Forgot to unmute. So how is this useful? So we can use this for image segmentation, actually. So the goal for image segmentation is to separate the foreground and background of an image as accurately as possible, as kind of shown in this image here of taking these sort of similar, sort of different pixels and then just defining them as two separate ones. So how do we actually do this in a graph? So in an image, we can make each pixel as a node, and then we can assign directed edges between, so every pixel has a weight to every other pixel next to each other, and then there's an additional two nodes that are the foreground and background. I think the next slide shows more about that. Yeah, so the source and sink in this case on the right side are actually the foreground and background nodes. So each pixel is connected to the foreground, and likewise each pixel is connected to the background by some probability that it can connect, that it is part of that foreground or background, and we'll go into how we determine that later. And then how do we use this is we need to figure out what are the weights for these edges. And we can use probability and a minimum cut to kind of say, okay, if there are pixels that are similar to each other, then we can make the weight between them pretty low. So not much flow is going between them, because we ideally want to cut where the pixels start to become different. So weight between like a pixel that's very light and a pixel that's pretty dark would be pretty high, because we were going to want to cut there. And then in the same time, we have some idea of whether a pixel is in the foreground or background. And then based on that, we'll have a high probability. If there's a high probability that it's a foreground, then the weight between a pixel and the foreground will be low, relatively speaking. Yeah, I guess I already mentioned that. So when we did our algorithm, we based it off of, I think it was like, I can't remember the names, someone in Jolly or something like that. But they essentially will find some probability that a given pixel is in the foreground or background using something called a Gaussian mixture model, which currently doesn't work properly and is still a little bit confusing to us. But essentially what that's doing is trying to find some distribution of pixels given, like if we know that some pixels are in the foreground and some pixels are in the background, then we can kind of use those colors to try to predict what the other pixels are. And then we can convert these probabilities into weights on a graph that we can use for this minimum cut. And then lastly, we'll cut this graph and segment the pixels into a foreground and background set. In the next slide, we have like an input. So right now what we're doing is we're using these scribbles on an input picture. So in this case, the red scribbles would be the background and the blue scribbles would be the foreground. And so we'll turn this into two different distributions where we're trying to find the mean and variance for all the foreground pixels, and then the mean and variance for all the background pixels. And then we can use probability, we use a probability density function to use the mean and variance to output a probability for every other pixel. On the next slide, we have our output, which still has some ways to go. I think we're not really implementing this probability theory properly yet, but it does cut the graph and creates two sets. I think we're just blending everything a little bit wrong, and we haven't finished that yet if we're gonna finish it. But this is kind of what we end up with, and we wish that it was more like what we would expect of like just the elephant popping out on one picture and just the background on the other. And that's all.